I don't know when will be published and if they will be published. Anyway, that I think are quite interesting about the concept of ventilator-induced lung injury that we heard in many different sausages and different recipes in the last 20 years, even more. Let me start with that. We know that if we have to induce a ventilator-induced lung injury in normal animals, we need, in normal lungs, we need tidal volume. The order of magnitude is 30, 40, 50, 60, 70 milliliters per kilo. And we know that in men, and you say, of course, this is men, but that is not so different, but we know that in men we have a dramatic difference of order of magnitude, because even, this is the classical review of the study, the classical study of 6 to 12 milliliters, even in a patient with a better compliance, that means in the patient more healthy, 6 apparently is better than 12. And 6 and 12 are not, 12 is not a tremendous ventilation, a tremendous tidal volume. With the 12 milliliters, in a normal man, we reach about, we almost double, we don't even double the lung size. And then we know that our lung may triplicate their volume if we take a very big breath. So, why this? Why in a patient, what is the discrepancy between the animal experimental findings and the human findings? And I think everything is back to the theory of Mead. This was applied, there was a Journal of Applied Physiology in 1970, and I strongly suggest you not to read, but to study this paper. That means to take a paper and spend hours in trying to understand what is a concept, that they try to summarize very easily. If we have a complete expansion of the lung is supported by the network of fibers. Each fiber is fully distended, and let's see the lung volume of each of these units is 10, which is 9 of gas and 1 of tissue. Now I decollapse completely one of these units, and the same applied force has to sustain now also the load that was sustained by this unit. So I have a greater force here, and this acts as a multiplier or force. In a simpler way, let's see, I have a weight suspended by 3 cords, 1 kilo. Each cord takes 1/3 of the kilo, 333 grams periodic. Now I cut 1 cord. The weight is always the same, and the weight is my, let's see, first approximation, transpulmonary pressure. But the 2 cords have to support 1/2 kilo each. That means the multiplication locally has been multiplied. And Mead say, okay, to go from the volume to the areas, which is the way the stress is expressed, you have to elevate to the power of 2/3. So you come out with this magic number of 4, and you read on the paper, locally, if you apply 30 centimeters of water on plateau, it comes out that you apply 120 locally pressure. This is theoretical computation, has never been measured. We try to quantify the possible multiplication factor, reversing the reasoning. That means we cannot measure the pressure into the lung, but we may measure the different distension. That means I cannot measure the pressure here, but I can measure the aeration here, here, and here. If it's here is 9 to 1, 9 to 1, 9 to 1, it means that the forces acting are homogeneous. If I have here 10 or 9.9, 9.9, and here 0 means an uneven distribution of forces. So when we were looking at each part of the lung, the aeration of one part compared to the aeration of the 9 bone units, we could find homogeneity or inhomogeneity. And we found that locally, as an example, in severe RDS, this unhomogeneity is related with everything, with the mortality, with the severity of RDS, with the low PO2, with the high PCO2. But that means give you an idea of what may happen into the lung. So the first notion is that when I apply the force into the lung is unevenly distributed. And greater is the unevenness of the unhomogeneity of the distribution, greater is the possible local damage. So in a healthy lung, I have more or less a lung which is homogeneous. In healthy lung, no. Now, if this is true, that means if exist into the lung foci or regions which act as a pressure multiplier, are the regions in which the distensibility is different. And where are these regions in a normal lung? We have around the visceral pleura, around the big vessels, and around the bronchi. So we reasoned, let's try to put pigs in a CT scan and to start with a ventilation that we know is lethal. That means when we reach the total lung capacity at each breath, we know that in 48 hours, the pig is dead with a huge edema. If the reason is correct, I should have the first lesion where the stress risers are naturally present. And we went to do this experiment. And you see here, these are the potential stress riser regions, okay? Now, and we have different possibility of lesions. Subpleural, which turn out to be the more frequent. The peribronchial, in which you can see the bronchogram here, and parenchymal, in which the vessels complicate technically to see the vessel in. Anyway, what we found is that during two things, that starting with the ventilation, for at least almost 6 hours, nothing happened. This big standard deviation is due to the fact that, if I have time, we'll explain that later. But you see, here is a perfect and normal pig's end expiration and at end inspiration. The inspiration, these were treated with a strain of 2.5. That means each breath was 2.5 times the FRC, as to ventilate a normal man with approximately 4.5 liters of tidal volume. 5 hours, 0. So if you stop the experiment, say, okay, the strain of 2.5 is perfectly innocent. Then, look here. You start here in the subpleural regions with a little things that at inspiration completely disappear. Then, and here are 15 hours, you see that this lesion increase and we have the appearance of many other parts. This becomes this unhomogeneity which multiply even the pressure. But look at end inspiration, everything is gone. Then 18 hours, some lung field is completely white. That means completely edematous. And end inspiration, we regain completely the aeration. At about 20 hours, all the lung at end expiration is completely white. look here, I never saw in man a recruitability like this. Only in Brazil, sometimes they have it. But, you know, it's completely white, and here is almost completely black. So that means that the lesion, this finding to me support two notions. First, that the lesion appears in the stress riser community, which fit with our previous reasoning and is not very surprising if the stress riser exists. But the second, and I didn't expect completely, these regions are completely recruitable. In these pigs, we had 12 pigs, well, 6 arrived with a pneumonia because they had an epidemic, but they look healthy. But at the CT scan was possible to see one density which was unrecruitable. These densities start to grow up even before the subpleural lesions, but the added density was absolutely recruitable, while the basic density, the core disease, remain dense. That means this locus of pneumonia acts as a very powerful stress riser. So the sequence is subpleural, basically, increase of subpleural regions, full lung. Here, everything is normal. When you start with this lesion, you start to have the lung mechanics, very small problem. And the gas exchange start to be impaired only when you have this kind of picture, none when you have this kind of picture. So, all VILI lesions are fully recruitable. And this reminds me what we found in man. Here in red, people with great with a low recruitability, which are the people, the recruitability is in green. You see the core disease in lower recruiters and higher recruiters, as with the pigs, is the same. But what was correlated with the mortality and everything was the recruitable part, which disappeared. So there are many possible explanations for that. But the possibility of the mechanical ventilation, of wrong mechanical ventilation, may add a recruitable density, with the pigs was very clear. I don't know with the men, but the reasoning is absolutely on the same line.
You have 1 more minute, Luciano.
So in 1 minute, I save you the real cause of VILI, and I'm ready for a question, which is not the stress strain, but is energy. But next time.
Now his presentation and those slides that never were presented are open for discussion. Any question, please, from the audience? There is a camera taking pictures for those who make questions.
Excuse me? No,
okay, if no question, so you can continue.
Okay, the energy, my dears, is the VILI. To hurt something, I need energy. And energy is not stress and strain. These are consequences. The real cause is the product of energy, of a pressure and volume, which is the energy, which goes into the lung. And part is dissipated here, in great part, is sliding the extracellular matrix, and part is undissipate. When we use PEEP, this is strain, which is little. This is PEEP. PEEP does not provide any energy because the delta volume is 0, is static. Energy is due at this part, so it's decreased, it decreased. With the same lethal ventilation at the end of the experiments, the animals are perfectly okay. And I want to continue. When we start to break the extracellular matrix, we have the hyaluronan and so on, which are fragmented. You are going to measure all these kind of components. They go through the toll receptors and they start with the inflammatory response. So I think, and we are confirming this using a little shot, but playing with the frequency. Lower is the frequency, lower is the energy. And preliminary results, more than preliminary results, fits with the theory. So to conclude, to protect the lung, we have two ways: less energy and more homogeneous, tidal volume, and so on. And this is what we may conclude from this topic. I thank you for the attention.